Okay, so today our lesson is projectiles. Projectiles. So the first question is, what's a projectile? So a projectile is a mass moving while under the influence of only gravity. All right. Let me put a little note here. In the real world, you'll find that air resistance is a factor in projectile motion. But often in physics, we are going to idealize the situation and we're going to ignore air resistance. Okay, the math gets way too complicated for our level if you're trying to include it in air resistance. The problem is, of course, that air resistance will change depending on how fast something's going. So you can imagine if you have an object, flying through the air and the resistance on it is constantly changing, the resultant flight path is going to be fairly difficult to calculate. You need calculus to be able to accurately model flight with air resistance. We have enough math to model it without air resistance. And really, probably for like the speeds and the objects we would deal with, it's okay to do that. Just keep in mind that we're sort of idealizing the situation. Okay. So what sorts of things would we consider to be projectiles? So projectile examples, or projectile motion examples. Well, there's like about 4 things maybe that we would consider to be projectiles. Some we've already dealt with when doing kinematics, like for instance, a dropped ball would be considered projectile motion. Okay. Or any object really, it doesn't have to be a ball. Balls are just easy to draw. And an object tossed up in the air that goes up and then falls back down would be considered a projectile. Now we've dealt with a few of these before. And what kind of links all projectile motion is the fact that the acceleration in the y-plane, this is the y-plane, right? Okay, the up-down y-plane, is always going to be equal to g. Okay, and of course g we take to be 9.81 meters per second squared towards the center of the Earth. So, seeing as how we're more or less on a flat plane because the Earth is so large, we just look at it like g acts straight down. Okay, just to kind of simplify our lives. Okay, so g acts straight down always. There's also a couple of other sort of more interesting scenarios, such as a ball that is launched horizontally from a high place, okay, and how it travels. Now we're dealing with kind of like 2 planes, right? You've got your y plane, or your vertical plane, okay, but now you also have your range plane, or your x plane. We call this often range, okay? The x-plane is often referred to as the range of the projectile. Okay. Now something to note about this. Does that look like a star? That is a horrible star. I need to do a better star than that. Something to note about this scenario. You have like 2 motions happening at once here, right? You've got motion that way, and that's going to be constant, right? If we ignore air resistance, we would say whatever velocity this object has to begin with in the horizontal plane is unaffected, right, by gravity, right? Gravity acts at a right angle to that forward motion. And then we have a separate accelerated motion in the y-plane, right? So we have an increasing velocity in this direction. And that ends up giving you those 2 things working together, right? Like a constant motion in this way, like ticking along as time goes by, okay? And then an increasing value in this direction, right? you kind of add those things up, and you get that characteristic parabolic arc. And then a little bit later, we will look at a ranged projectile. So this would be something that is, I mean, like say a kicked football or a thrown baseball or something that is, essentially launched at an angle. How does it fly? How high does it go? How far does it get? And so on. Okay. And this, much like this, actually, you can kind of think of these as sort of related. This mimics kind of the last half of the travel of the football, right? And because we're ignoring air resistance, we would end up with a very symmetrical kind of flight path for an object like this. Okay, so we've got our range in the x direction. Of course, again, no acceleration in the x, but a constant downward acceleration equal to g, right, in the y. Okay, um, problems with drop balls and thrown up and down balls, I think we've covered fairly well with kinematics, but just to make sure we're comprehensive, let's throw in a couple of examples that we might find. Okay, one. So the ball is dropped from a 100-meter high tower. And I could ask you to A, find time to ground, and B, find final velocity. Now, often in problems like this, that's all you're going to be given. It's up to you as the physicist to know G is going to be acting here, right, in that vertical plane. So this is accelerated motion, right? So we have to access the formulas that we use for accelerated motion. So that's one way to write it. We usually do this, though. Just different ways of writing the same thing, okay? And then we also have this possibility. All right, so these are going to be kind of what you need in order to solve this problem. All right, so I'm going to just pause for a second and let you give it a try. All right, so we'll realize then that the initial velocities in both of these cases is 0. So if you have a 0 value in here, I mean, that just cancels out t, right? 0 times t is 0. And then we just do a little algebra, right? 2 times d gets rid of the half, divide by a, and square root to cancel the square over there, and you get 2d over g. Okay, the acceleration here, in this case, is the acceleration due to gravity. So that's a matter of, putting in the correct values from the problem. So your time should be equal to root 2 times 100 meters divided by 9.81 meters per second squared. Now, some people are going to be like, but what about the negatives? Okay, like this is all downward. So let's just address that. Here's how I kind of think about the negatives and the positives. Just give me a sec here. I want to draw a little tower. Okay, so, we have this tower. It's 100 meters high, right? Now, we know when we're dropping something, it's moving in this direction, right? So it's delta position change, right? It's delta d. It's actually its final position 0 minus its initial position 100. It's actually negative 100 meters, right? And then acceleration g is acting in that same direction. So as a physicist, right, we have to understand that we're kind of like setting orientations with our our own brains. We can decide whether we want down to be negative or down to be positive, okay? If you're a stickler and you can't handle that and you want to do it by like rote memorization, and I always say that down is negative, that's absolutely fine. Go ahead and put negatives in here. You'll notice that you get double negatives. It does not change your answer, okay? Something to realize, of course, mathematically is you can't have a negative under here. You know, just depending on your views and your physics teacher and how you like to work with things, I'm gonna, you know, let that be your sort of prerogative. Now, where negatives and positives are important will be later. Like, for instance, if we throw something upward, right, and G is downward, well, now we have to have a positive on this and a negative on this, or actually vice versa will also work. You know, the reason being is because these are vector values and they're acting in opposite directions. So the negatives and positives are going to be a factor there. That's where it is important. So in a problem like this, it doesn't matter, and you have to understand why it doesn't matter, okay? Or why in other problems it does matter, okay? You know, I think like a healthy dose of common sense in here is really quite important. If suddenly a negative value pops up underneath a square root, you know, alarm bells should go off. You know you've done something wrong. It's like if you're trying to deal with angles and negative values are coming up when you do sine and cosine. Well, an alarm bell should go off because you can never have a negative value when you do sine and cosine unless your calculator's in radian mode, which unfortunately happened to someone on our last test. So you got to watch for things, right? You got to have a healthy dose of common sense. You got to be very aware of what's going on. If you're not, you're space monkeying, right? You're just throwing numbers at formulas and crossing your fingers. Terrible way to do physics. Don't be that person. All right, so anyway, so VF, we should be able to solve here as 2. Like I said, your displacement is negative, G is negative, so they're in the same plane. I'm just going to call down positive, and realize that my final velocity is in the downward direction, and we'll just, you know, insert that information at the end. So we got root 2, 9.8, of course, realizing we're talking about down, and 100 meters. We should put meters per second squared. And then we just solve. Okay, so here's our values. 4.51 seconds, and a final velocity of 44.3 meters per second, of course, in the downward direction. Okay, let's look at the second type of problem we might see in the just dealing with the vertical plane, right? Vertical only. Actually, I don't even think we'll introduce the horizontal today. We'll just strictly stick with the vertical stuff. Okay, so how about this? A ball. Always a ball, right? A ball is thrown upward at an initial velocity of, I don't know, 25 meters per second. Calculate a time to max height, B, max height, and C, total air time. We'll make one assumption here, assuming, my writing's getting messy, ball returns to origin. Okay, so you're gonna have to reach into your bag of tricks from kinematics, and you're gonna realize this, first of all, that as the object travels up, your time to max height is gonna be found via this formula. Now, why is that? So if you think about it, as the ball goes up, it slows down, right? So it's got an initial velocity, it's got a final velocity. You know when it's at its maximum height, that final velocity has dropped to 0, okay? We know from past experience that velocity is defined as, I'm sorry, it's not quite right. Acceleration is defined as change in velocity over time. Now the acceleration we want to deal with is g, so we rearrange our formula to look like this. We say this with time. We know the final velocity is 0 meters per second. we know the initial velocity was, what did we say it was, 25 meters per second. And this is an important scenario where direction does matter, right? Gravity is in the opposite direction of velocity, so we have to end up making it negative in here, right? Or we'd end up with a negative value for time, okay? So I think we should get like just slightly over 2.5 seconds. Is that correct? Put 2.55 seconds, my people tell me. So now we know that this is time to max height, right? Now we can figure out how high that is. So remember, this object is under the influence of gravity. So if we want to know the distance that it traveled, probably the easiest way to figure that out is just using this old guy right here. Vf plus Vi over 2 times t. So final velocity is 0 plus 25 meters per second divided by 2 times that 2.55 seconds. So you should get about just slightly under 32 meters. Okay, so about 31.9 meters up. So that's how high it goes. Now, the last thing I want to do is I want to figure out how much time it takes to come down. Now, the little secret is it's going to take exactly this amount of time, but let's just prove that to be true, okay? So there's kind of different ways to prove it. I think one way is probably just to rearrange this formula and solve for t. So actually, we just use our formula that we derived in the first problem there, right? Which is t is the root of 2d over a. So 2 times 31.9 divided by g, you will find gives you 2.55 seconds. So the time up will always equal the time down. Now, you might get a slightly different value due to rounding, but with no air resistance, gravity's acting the same and you have a symmetrical flight, okay? We're gonna probably leave it there for now, and we'll come back to the ones with some horizontal components next time. And I just realized that we didn't put in total air time, so it's 2.55 up, and then 2.55 down, so 2.55 times 2, which is what, like 5.1? 5.1 seconds.